And exactly using this, some theorem is proved, which we will not prove here. It says that suppose f is a continuous function from closed interval a b to r. So, automatically it is bounded, that we know. It is a closed interval a b. Now, its restriction to sub intervals, its restriction is also continuous. So, f achieves maximum, f achieves minimum inside every sub interval, right. Now, the upper sum and lower sum are well defined, because maximum and minimum exists for any partition a b. So, what the result says that f x is integrable, so that this integral is a real number in case f is continuous. So, that is our result. What does it say? If f on a b to r is continuous, then f x is integrable. So, that is the main result, which uses our notion of this summation of capital M I minus small m I into x I minus 1 goes to a limit, that limit exists and that is equal to 0 when norm of this partition P goes to 0. That can be proved by using only continuity of the function f on the closed interval a b. So, when f x is continuous on a b, it is integrable. We accept this result. Further, you see, in that case we are really getting the signed area. Okay? And what is that signed area? Area of the region is, what is the region? It is the region bounded by the curve y equal to f of x, the x axis and the lines x equal to a and x equal to b. It is the signed area. So, when you go for the computing the proper area, the geometric area, that will be integral a to b mod f x dx. That also should exist, because they are just signs. So, you can compute them and add them together after taking the absolute value. So, this is the basic idea of the area and integrability. We will see what does it mean. Our result we can state now. Let f from a to b closed interval to r be a continuous function. Then both f x and mod f x are integrable. Further, integral a to b mod f x dx is the area, and integral a to b f x dx is the signed area of what? Of the region bounded by the graph y equal to f x, the x axis, the lines x equal to a and x equal to b. That is what we have discussed. Now, we will be looking at some problems basing on this, but just a bit. You can always compute this area by choosing any partition P. How are you going to compute this area? First, we choose any partition P, and then once you know that it is continuous, it is integrable, you choose any C I in between that x I minus 1 to x I in the limit that should be same, right. That is proved here in the theorem. So, that means we can choose any convenient choice set C, choose a partition, then inside each sub interval choose any convenient point C I, then take the Riemann sum and then take the limit as norm P goes to 0, right, as each x I minus 1 and x I difference goes to 0. So, that is what we do for computing the integral. So, you may choose something like, as a particular case, you can choose your partition to be a uniform partition, that is it a to b, you can divide into n parts, each part is having b minus a divided by n. Okay. Suppose it is a to b, you want to divide it into 3 parts. So, you can say it is length is b minus a by 3. So, it will be a, then a plus b minus a by 3, a plus b minus a by 2 into b minus a by 3, and this is b of course. So, then you can choose any choice point, maybe left side, that a itself can be a choice point C1, or maybe right one, which is x I equal to C I. Those things we have the choice to make. Anything is convenient for we can take, provided the function is integrable. So, its limit also will be same, that is why this happens. Then what happens? If you divide that into n parts, we want this norm of the partition go to 0. So, that means each one is b minus a by n, that goes to 0. So, n should go to infinity. That means, if you take this Riemann sum after this choice and you take n approaches infinity, the limit will be equal to the required integral. This is a particular case of that. Sometimes we choose like this if it is easier, or sometimes we choose other Ci which will be convenient for us for computing the integral. Okay, let us see how to compute this integral 0 to 1 of the function x. So, integral 0 to 1 x dx. So, how do we proceed? First of all, we know that integration is possible, the integral exists. So, what do we say? F of x equal to x is continuous on the closed boundary interval 0 1. So, we apply our theorem, therefore, we conclude it is integrable. Then we can choose any partition, let us choose a uniform partition. So, say p equal to 0, 1 by n, 2 by n, n by n. So, there are n plus 1 points, you have n number of sub intervals. Now, we choose C to be the right end point. You could have chosen even the left end point, does not matter. So, suppose I choose the right end points, then the Riemann sum is exactly the upper sum because it is x equal to x. So, right end point will be bigger value than the left end point or any points inside the interval xi minus 1 to xi. So, that is really the upper sum. It is f of Ci into xi minus 1. Now, what is f of Ci? Ci is I divided by n. Okay. So, f x equal to x. So, f of Ci equal to I divided by n, and then the length of the sub interval is 1 by n. Now, you see it is 1 by n square into summation of I. Summation I from 1 to n is equal to n into n plus 1 by 2. So, divided by n square, that gives n into n plus 1 divided by 2n square. So, this we can express in the form half plus 1 by 2n. Now, when n approaches infinity, that should give us the integral, because in that case our norm of the partition which is 1 by n goes to 0. So, we take n goes to infinity of this expression half plus 1 by 2n, and that gives us the limit as half. So, that means this integral is equal to half. That is what we have computed by using the definition and choosing one uniform partition. But most important, this sentence that f x is continuous on the closed bounded interval 0 1, therefore, it is integrable. So, we can choose any particular types of partition like uniform partition or not uniform, and then we can choose any particular choice set C, and then take the limiting process to arrive at the answer. Of course, if you choose different Ci's, it should give the same answer, it will give. Okay. Let us take another example. Suppose we have the constant function f x equal to k, k is some real number. Then we want to see that its integral will be equal to k into b minus a, right. So, intuitively it is very easy to see, but we see we want to verify whether our intuition really going along with our formal definition or not. So, say a to b, we have a function which is f x equal to k, it looks something like this, it is k, right, throughout. So, when you take the area, it should be this rectangle and that should be equal to k times b minus a, right. That is why we write. So, that this is so by using our formal definition. Okay. So, what we do? First thing is it is continuous. This function is continuous on the closed interval a b. So, it is integrable. Therefore, we can choose any partition. Let us choose a partition p equal to x0, x1, xn. In the abstract, we are not giving exactly what values they are. That will not be material here. We will see. So, now we choose Ci equal to xi. Again, the right end point. You can choose left hand, you can choose anywhere because the function is constant anyway. So, any Ci also will give the same computation here. Now, in each sub interval xi minus xi, you choose Ci equal to xi. Okay. Now, the Riemann sum with respect to this is summation f of Ci xi minus 1 and f of Ci is equal to k. So, that is the summation. But this is now, it is really summable, right. It is something like if you expand the summation, when k equal to I equal to 1, it looks like k into x1 minus x0 plus k into x2 minus x1 and so on plus k into xn minus 1. So, you see that this first ones x1 and here it is minus x1. So, these things are cancelling, right. So, that means whatever remains is k xn and k x0. okay? Everything else cancels away. So, that is equal to k into x n minus x 0, which is simply k into b minus a. Therefore, when you take the limit of this where norm p goes to 0, will be again that because it is a constant. So, we get the integral equal to k into b minus a. So, that is simple, it is a verification of our definition for this easier case. Okay. So, let us take not very easier case. So, evaluate the integral a to b cosine x dx. So, first thing is integral exists, and that is so because cosine x is continuous on the closed interval a b. So, it is integrable according to our theorem. Now, we choose any partition p, which is say a equal to x 0 less than x 1 x n equal to b. Let that be a partition. We have to choose some c I so that we can compute the limit, right. So, here we will choose our c I in a very specific way, and that answer should be same because the function is integrable. In what way we are choosing? So, you will see why we are choosing this way shortly after the computation comes. Now, look at the function g x equal to sine. This is just a trick to get that Riemann sum evaluated. Otherwise, you may have to refer to difficult limits. Now, look at the function g x equal to sine x. This is continuous on each of the sub interval x I minus 1 to x I, closed interval, and also differentiable on the open interval x I minus 1 to x I. Okay. Therefore, we can use mean value theorem. By mean value theorem, there exists a point in between x I minus 1 to x I such that g of x I minus g of x I minus 1 equal to g prime of c I into x I minus x I minus 1. Okay. Is that clear? That is mean value theorem. So, this says sin x I minus sin of x I minus 1, which is g, that is derivative of sin, which is cosine of x evaluated at c I. So, that is cosine c I into x I minus x I minus 1. Now, what is cosine c I? Our f of x is cosine x. So, it is f of c I into x I minus x I minus 1. So, that is the advantage in getting this c I. Now, we have to take the Riemann sum. So, we will choose our points c I, that choice set, as these c I's, fine. So, with this choice set c equal to this c 1 to c n, we have the Riemann sum, which is f of c I x I minus x I minus 1 summation, that is now equal to, because of this, equal to summation sin x I minus sin x I minus 1. Now, as earlier in the constants case, you see it is sin of x 1 minus sin of x 0 plus sin of x 2 minus sin of x 1 and so on. So, many things cancel out, only the first and the last remain. So, you get sin of x n minus sin of x 0, that is sin b minus sin a. So, once we are able to evaluate this sum and get sin b minus sin, it is a number now, right, a and b are fixed. So, when you take the limit of the Riemann sum, that will be equal to that number itself, fine. So, integral a to b cos x dx equal to sin b minus sin a. Now, you see our question was which function it is, f of x, whose derivative will be equal to this small f of x. So, now you see that function should be sin, that is what it says, right. So, specifically in this integral, if b is a variable now, variable point, you would say sin x minus sin a. So, that is our f of x. F of x we can take to be here sin x minus sin a. So, it will really solve our purpose, but up to a constant. So, this constant comes from the lower limit a, fine. So, it is going very satisfactory way, because that was our aim, to find such a function capital F of x whose derivative is this, and by defining the area we are reaching this integral, and that integral may solve this, but that we have to prove separately, right. That really serves the purpose of getting a reverse process of differentiation. Okay, before that, let us solve some more problems and see how it goes, how our definition goes. So, the idea is that it is, if it is continuous on the closed bounded interval, then it is integrable, but there can be some where it is not integrable, fine. Like if it is not continuous, it does not mean that it will not be integrable, but here is an example where it is not continuous and it is not integrable. So, we give this function f of x equal to 1 if x is a rational number between 0 and 1, and it is 0 if it is irrational and between 0 and 1. So, f is defined on 0 1 to R. In fact, its range is only 0 and 1, nothing else. Okay. So, now this is a bounded function because it assumes only two values 0 and 1. Now, let us take any partition, you can choose any partition, does not matter, and let I belongs to 1 to n. Then what happens? You can see that the maximum of f of x is equal to 1, because in every sub interval there are rational numbers, and its minimum is equal to 0. Similar reason that in every sub interval xi minus to xi there is an irrational number. So, minimum becomes 0 and maximum becomes 1. So, when you take their difference, okay, or the upper sum you can say instead of the difference directly, upper sum is 1 and the lower sum is 0. If you have taken the difference summation of mi minus small mi xi minus 1, that would give rise to 1. Then in the limit it will never go to 0 because it is 1 everywhere, therefore, it is not integrable, right, as norm p approaches 0. Whatever partition p you choose, it does not matter. So, here is one function which is really not integrable, we cannot find some f. So, f prime will be equal to this, that is the basic idea, but we will come to it. Okay. So, let us take another problem to check whether we are really computing nicely or not. So, here it is asked to find the lower sum and the upper sum for this function f defined on the closed interval 0 1. What is the function? It is x square. Okay. So, we want to find the lower sum and upper sum by dividing this interval 0 1 to n equal sub intervals. So, this is in between our problem of going for the computing the integral. So, let us find the lower and upper sums. We have the partition as 0, 1 by n, 2 by n, n minus 1 by n and 1 last point, right. 1 by n is the uniform, each sub interval has the length 1 by n. Now, x square is an increasing function on 0 1, it is increasing from 0 to 1, that we know. Therefore, when you take the lower sum, it will be the left end point, that is your C I, and when it is upper sum, it will be the right end point which is C I, that is will be x I equal to C I there. Okay. So, in the sub interval I minus 1 by n to I by n, that is our sub interval, the minimum is on the left, that is I minus 1 square by n square, and the maximum is on the right point, which is I square by n square. Therefore, the lower sum is summation of f of that lower end point where minimum is achieved, that is I minus 1 square by n square into x I minus 1 by x n, which is 1 by n. So, that gives I minus 1 square divided by n cubed. Okay. So, this is 1 by n cubed comes out, we have summation of I minus 1 square I from 1 to n, that is summation of k square, k is from 0 to n minus 1, right. So, we apply that formula summation k square, that gives summation from 1 to n minus 1, that gives n minus 1 into n minus 1 plus 1 into 2 into n minus 1 plus 1. So, that gives 2 n minus 1, that is n minus 1 into n into 2 n minus 1 by n cubed. Now, this you simplify, it gives to 1 by 6, 1 minus 1 by n, 2 minus 1 by n, 1 n cancels here, and then 1 n goes inside and gives this. And when you take the upper sum, it will be I square here, instead of I minus 1 square, it is I square by n cubed, I varies from 1 to n. So, it will be like this, that will be n into n plus 1 into 2 n plus 1. So, when you do similar thing, it will be plus really, not minus, 1 plus 1 by n, 2 plus 1 by n. Now, if you take the limit of the lower sum and the upper sum, of course, you get to be 1 by 3, right, both the limits are same. So, therefore, this is integrable because we have got it, but only for the uniform. Okay. So, if you take some other sub intervals, it will also be like that, it will be behaving similar way, because you can take x I and x I minus 1 and then, but summation of xi minus square will not be able to evaluate unless we know xi to xi minus 1. Of course, you can show this later that sum will be 1 by 3 even if you take other partitions, but our problem does not ask that. Fine, we want only n equal subintervals. Okay. So, let us go to second problem. We have a function which is continuous, f of x is continuous function. Okay. So, now we want to see that, see f of x we have not given the domain, it can be any domain, maybe if nothing is given we may think of f from R to R or any convenient thing which will be required. We want to show that summation n goes to infinity I from 1 to n, 1 by n, f evaluated at 1 plus I by n minus 1 by 2 n minus f evaluated at 1 plus I by n equal to 0. So, now you see I has to be in between 1 to n. So, if you take I equal to n, that will be the maximum value of this point 1 plus I by n minus 1 by 2 n, that will be 1 plus 1 minus 1 by 2 n, right, 2 minus 1 by 2 n. So, when you take n goes to infinity, that will give 2. So, it looks that we have to define the function from the interval 1 to R, okay, to evaluate this limit. Fine. So, let us try say function f from 1 to 2 to R. Consider its restriction, because nothing is given, we have assumed R to R. Now, you think of the restriction that f is a function from 1 to R. Now, we take a uniform partition of 1 to 2, right, say 1, 1 plus 1 by n, 1 plus n minus 1 by n, and last point is 2. Then formulate the upper sum. So, the upper sum is 1 by n into f of upper sum will be where? It is not really upper sum, it is sum at the right end point, because upper sum means the function should achieve maximum value. We do not know, because f is not given to be increasing. So, it is not exactly upper sum, it is one of the Riemann sums, right. So, consider the Riemann sum. This is a Riemann sum where we choose C I equal to x I, the right end point, that is equal to 1 by n, f of 1 plus I by n, right. So, n from 1 to n. For example, here it is the right end point we are choosing. So, all the right end points we have chosen. Now, when you take the choice point C I as the midpoint of the subinterval, that is x I minus 1 to x I, you choose the midpoint. So, that midpoint is 1 plus I minus 1 by n plus 1 plus I by n divided by 2, that is the midpoint. So, that gives you 1 plus I by n minus 1 by 2 n, which is asked here. So, that is our C I, and that is one particular Riemann sum, and this is one particular where C I is chosen as the midpoint. So, we can see that the expression here we have, it is called this point as T I, the right end point is x I really. So, it is summation Riemann sum where C is taken as the right end point, set of right end points, and the first one is where C is taken as the set of midpoints. Okay. Now, you see this is a continuous function on the closed interval 1 to 2. So, it is integrable, right. Once it is integrable, you choose any two Riemann sums, okay, for the same function defined over that interval and so on, that should go to 0 or norm of the partition goes to 0. Fine. So, that is what we are doing. Since f x is Riemann integrable on 1 to 2, each of the above limits exists and it is equal to the integral 1 to 2 f x dx. Therefore, the difference must be equal to 0, right. So, that is how we will be solving some problems by identifying this expression in n with some Riemann sum. That is really the clever part here, and that you will get acquainted slowly. Okay. So, let us stop here.